quite a number of technical problems, and I hope you can hear me, and welcome to the finalization of our exercise. So the design task is to make a gas analysis sensor, and as it is has been several days since we did that, or we started that, I will be repeating first the task. So we have a thermal microsystem with a MEMS heating plate, 5 by 5 millimeters square. The plate hangs on 1 millimeter long bars above a cavity that has been deep etched into silicon. So typical silicon bulk micromachining and surface micromachining techniques. Chip is 10 by 10 millimeter. We have a power dissipation of 5 watt in the plate, and that is continuously. We have a maximum operating temperature in the heater of 570 degrees centigrade. And on top, we have free convection, and the surrounding air has a temperature of 50 degrees centigrade. So in the thermal management calculation, we will have to take that into account. The controller is available as an ASIC with an analog part. We have the versions either a bare chip as a flip chip, or alternatively a surface mounted device. And we already have designed that. We have a maximum junction temperature of 150 degrees centigrade and a power of 2 watt. The lifetime we would like to have for the solder joint is more than 1000 temperature cycles up to 150 degrees centigrade. And you must, for that, also you must select an appropriate substrate temperature. Yes. Your task is to make a system concept for the complete module with the devices. We have the package type for the sensor. We have the package type for the controller. We have substrate carrying and interconnecting the devices. We have the assembly and mounting techniques of the devices. We have interconnection techniques for the sensor, and we must protect the complete assembly. Yes, there are no gas ducts, of course. That's sorry. We had a gyroscope, didn't we? Oh. Oh. Okay, so then, but do you have the data for that task? Okay, sorry. Then somehow it was mixed up because I had to copy that, to the other screen size, otherwise it would not work. Okay, so here we see the overview, and we have a housing. That housing is made of PA6. It's a injection molded housing. We have a lead frame, which is copper iron 2. It has nickel gold plating. We already defined why we have that. We have a silicon substrate. Here we used here a special technique for the substrate, and here is the MEMS with the gyroscope. Here is the device we have, which is a QFN device, which was also already produced by us. And yeah, what else do we have? We have the bonding wires, and in that way we had to accomplish the different parts. We have the package of the IC, we have the substrate, we have the package for the module that had to be produced. We have to assemble the sensor on the substrate. We have to assemble the IC on the substrate. We mount the substrate in the package. We do the interconnection of the sensor, and then yes, after that was interconnected, of course, we have to fill with silicone. And finally, we do the enclosure. Also, the silicon can also be hardened at that time, could also be hardened later. We do it here, we harden it. We do the enclosure. That means lid and welding. Okay, then we should be finished. So that was the overview. In the exam, please first make an overview. If you don't do it, you might forget an important point, and that could cost you 6 credits or more, and that is having an effect on your mark you get. Yeah. Okay. So we had the QFN. We produced it until we had it ready. Then we had the substrate. Then we had the sensor chip. We did it on a wafer. We created a structure with surface micromachining. We have a cap wafer that is produced with bulk micromachining. That means anisotropic etching.
Yeah.
You have a question, please? Hello? Okay. Then we must heat out, and then we do the wafer bond, for instance, with glass frit. And that would mean, for instance, having a temperature, let's say, of 450 degrees centigrade and 15 minutes in vacuum. The reason is for a gyroscope, we do not want to have damping because that would degrade the quality factor and the accuracy, and to that purpose, it must be closed in vacuum. Okay, so then we have the substrate. And the production, and what we wanted, that was your wish, we wanted to have a silicon substrate, and we have a silicon carrier, and we want to have a copper. But what is important, as we later on are going to solder the QFN on it, yes, we need copper that is thick enough, maybe somewhere between 10 and 15 micrometers at least. And the question is how to get such a thick copper. And the buzzword is semi-additive technology. Semi-additive, as we know, it means both bringing something on, but also taking something away. I would call it subtractive additive, but I don't know. That is the terminus. Okay, to that purpose, we first must bring on a starting layer, all on the wafer or on the silicon part. Typically, we have a first layer of titanium or chromium in order to improve adhesion. Then we start with copper in the same process because we do not want to have oxidation of the titanium. So we do it just in the sputter machine, switching over. Then we have 1 micrometer of copper. After that, we take it out of machine, we spin on a photoresist, expose it, and develop it according to our structure. Then we electroplate the copper in a thick way, and we electroplate also tin. That is a so-called etch resist, because in an acid that etches the copper, it will hardly etch the tin. Yeah, and then we strip the resist and we back etch the titanium and the 1 micrometer copper. And after that, we can also etch away the tin. Then we can have a chemical metallization of nickel and gold. And in that way, we have a structure which is only a one layer metallization structure of silicon and having, for instance, 10 micrometers or so of copper on that silicon. Okay. After that, we can spin on a solder resist that is necessary, and it is exposed, and so it's hardened. Exposed and developed, and in that way, we can have our structure. So that was the substrate. Then we have the package itself, and that's the package of the complete module. What do we need here for the package? We have seen it in the beginning. We need the package body. We need a lead frame. We need a lid. And we have the heatsink. So first of all, let's start the lead frame. We have a CAD design, and then we start with a sheet of that material. So that's big panels, only 0.5 millimeter thick or so. And in a special tool that must specifically machined, we have something that can stamp and bend our sheet. And then we also must produce a mold, which is the negative form of our package body. And we also, yes, of course, we need 2 molds, one for the package and one for the lid, of course. And then also we must design a heatsink. So with that tool, we punch and bend the lead frame. The heatsink is machined by machining operations and drilling and grinding. And then after that, the heat sink typically will be plated with nickel, for instance, with a chemical or electrochemical process in order to protect the surface. And okay, also the tool has been produced, and we place the heatsink and the lead frame into the injection molding machine, and we injection mold. For instance, having a temperature of, here I said 250, but it can be up to 350 degrees centigrade for the extruded material, and the tool typically has 80 degrees centigrade, and when we inject, the polymer is consolidating, and in that way we have the part. Then we can injection mold the lead, and as a last step, we can, for instance, chemically plate all metal surfaces. So electroless. Yes, only the metal surfaces with, for instance, with nickel gold. That can be done on the lead frame after the molding or before the molding. Okay. Then we proceed where we wanted to go ahead. And yes, what was our decision to do the mounting of the surface mounted device? It was soldering. But what was our decision for the other device, for the MEMS? What did we say? We also said SAC. And now the question is, how do we perform such a process? For both, it's a SMD process for both devices. And yes, the solder will be SAC. And here we have a stencil. That stencil must be produced. First, we have a CAD of our substrate that we already have. Based on the CAD, we can also design a stencil, which is just the negative of the metal pattern that is done by some service company. And after we have that, we place the stencil on top of the substrate. We put on a certain amount of solder paste, and that squeegee is moved over the stencil, and the paste is pressed into the openings, and in that way all copper or nickel or copper nickel gold surfaces are coated with solder paste. Okay, so we stencil print, and then we pick and place chips, and then the soldering is done. What I would like to see is a typical solder profile. What's the temperature of soldering which we have generally as a rule for soft soldering. What is it? That is correct. I write that here. Generally, we can say it's a T liquidus plus, let's say, 20 Kelvin. Also can be 30 Kelvin. And in that way, it's roughly 220, the liquidus for that solder. And then we have a certain profile which goes in that way. So that's a short time, maybe 10 to 20 seconds. That is possibly 2 minutes or so. So that's always depending, but that's the order of magnitude. And here we have a preheating, let's say around 150 degrees centigrade. And so in the range where the solder is accomplished, we have only a short time and we must reach that rapidly, but we must have sufficient preheating of the complete assembly. Otherwise, the cold parts would just pull away the heat, and so it would not solder properly if the temperature is too cold. So that's the way it should be, and that's a typical solder profile. So here we have the temperature in degree centigrade. Okay, that's the soldering. And we have done that for both devices. So we do not have an additional process. So let's go back. What the next step is. Yes. Now we mount the substrate in package. That is an easy one. How would we do that? Now keep in mind, we have a silicon substrate and we mount it on a copper plate. Could there be a problem? What could be the problem? What is the CTE of copper and what is the CTE of silicon? And in that way, we could have CTE mismatch problem. And how can we deal with that problem? So that is the substrate. That is the copper. What do we have to put in between and not to have too much stress? Yes, and what kind of adhesive? I would say we use an adhesive that is quite flexible. We don't have to make that sketch in the, but that here is a flexible adhesive. For instance, it could be a silicone. And silicone means for instance, with low filler or with no filler, and that means it has a low Young's modulus. Okay, but the question is how we do it. Possibility is screen print adhesive, or we can also use needle dispensing. Pick and place we can place the substrate, and then what will we do then? So the glue is still liquid. Harden, yes, of course. Which just to have a guess, 120 degrees centigrade, 2 hours, for instance, that would be something reasonable. And in that way, that has been accomplished. So what's the next step? Yes, normally almost all adhesives have some filler in it. That is either particles or it can be silver or such a thing. The more filler we have in, the harder it is. On the other hand, advantages are higher, lower CTE, higher stiffness, if that's sometimes an advantage, higher thermal conductivity, but here it's a large area, bad CTE mismatch problem, and in that way, we would take such a softer material. We also could maybe use an unfilled epoxy. There are also epoxies of low glass transition temperature, for instance. Yes. What's the next step we have to go for? What is missing now? You can do that, but then your device will do the same as my Beamer did recently. Nothing. Why so? What is missing? Yes, of course, we need the interconnections. Yes. We already decided on that. What will we use here? Sorry? No, that's not, that's for the lead frame, for the interconnection. Gold wire bonding. And So what I would like to see is maybe a sketch of how it looks, the wire bond, and a description of the steps and what are the relevant parameters for wire bonding. So it is gold. Diameter is typically 25 micrometers. And yeah. Sorry? Yes, gold. Why? Because it's corrosion resistant, because it bonds to almost any bondable surface. That would be one. 25 micrometer wire bonds can already carry sufficient of current we need here. Yes. Of course, you can also, in most cases, you can also use aluminum wire bonding with 25 micrometers aluminum silicon, while you also use aluminum wire bonding for thick wires, but then it's another alloy and it's a somewhat different machinery you use. Sorry? Because we decided to do gold. Yeah. No, if you describe it reasonably, you cannot do anything wrong. Yeah. Okay. So, yeah, I do it against the substrate. That's easier. And so here we have something gold plated. We have something on the chip. We typically have aluminum. So we have the wire bond. Yeah. That's a bond. And now we describe what the steps of bonding are. So the initial step is flame off of wire end. That is done with capacitor discharge. And so we form a ball. Second is press ball on chip. How do we call the process? So we do a thermosonic bond. Then third step is we transfer the tool. So we form a loop. And then we do the wedge bond. that is here. And the last step is we tear off wire end. And then we go to step 1 again. Okay. And in that way, we have performed the bonding. For what do we do the bonding? So that's both for chip to substrate and substrate to lead frame. What is still important is bonding parameters. What are the 4 bonding parameters we have? In thermosonic bonding? So we have the tool. And what is the tool doing? We press. And for pressing, what do we need? Which physical property? Force. Yeah? What's the tool also doing? Typically, it's not heating the tool. It vibrates. And we have the ultrasonic power. The heating is coming from the substrate. We have a temperature. And what is parameter number 4? How long does it take to do one bond? 1 hour, 1 minute? What? Yes. So the last parameter is time. Yes. So we have force, power, temperature, and time. Force is typically in centinewton. You could say in grams. Power is typically in 1 watt or so. Temperature is typically 150 to 300. And time is typically, let's say, 20 to 50 milliseconds. So that's typical data. And in that way, bonding is accomplished, but it is important to know at least what the parameters are in principle. Okay. We have performed the interconnections. Then maybe we come to the last step. That was number 8. We fill with silicone, so enclosure and silicone filling. So fill package with silicone Don't forget the E here at the end. Gel, harden. Again, we could do, for instance, the 120-degree 2 hours, for instance. That would be something reasonable. Then we put on lid. And then we can do some welding. So it's typically a fusion welding process. And in some way, we want to create here a tight weldment. Fusion means something is smelting, and then that can be ultrasonic or laser, or just take a hot tool. What you could also do is glue it on, but normally gluing to injection molded parts is not so easy. Okay, so we should be finished. Second to think it over all together. And now we will be going to the calculations. Unfortunately, I copied in the wrong design task, but so I have to repeat it now. Enclosure and lid, so we have that. Yes, here are the conditions we have. The IC has 10 watt of power dissipation. It must stay below 135 degrees centigrade, and the environment is 50 degrees centigrade. And then the stress must be below 75 megapascal, and the solder joint has below 1,500 cycles. Okay, so we have defined what our design target is. Now I have to just put in a few blank Okay, so first of all, we have the thermal management of the whole system. And the task is power is 10 watt. And the T of the environment is 50 degrees centigrade, and the T max is 135 degrees centigrade. So question is, how will we solve that problem? So give me an idea what we have to do. You can prove that, but how will you do it? How can we determine the temperature our device will have? The temperature of the device is how much? Is it depending on the power? Yes. What else is it depending on? Yeah, but the area is part of one property. What's a property defining the thermal behavior of a package? The thermal resistance, of course. And what else do we have to take into account? No, because it's not a heating problem. It's just a steady state problem. Heat capacitance, we only need in cooling or heating up processes. Yeah, but the temperature we have, it's depending on the power we dissipate, it's depending on the thermal resistance, and what else is it depending? Does it make a difference if the device is working at the North Pole or at the equator? Yes, plus TU. And that as a must be smaller than the Tmax. Okay, that's a condition. When you meet that condition, you've fulfilled your design task. Okay. In that, if we say it's an equation, what is unknown in that equation? Yes. So that's your noble task, to find out what the thermal resistance is here. And then you can use your equation Sometimes people also say the thermal resistance of the device must be lower than some critical thermal resistance. The disadvantage of that solution, so it's not wrong, but the disadvantage is that I do not explicitly see the maximum temperature we have. Yes, then I only know it's below 135. So it's better to really calculate the temperature. Okay. Now the question is, how do we get the thermal resistance? And then we can have a look at our assembly. Here is a silicon chip. That silicon chip is die attached on a heat slug. That's a QFN. The whole thing has a polymer on top. On top is the silicone, and on top is the lid. Yeah. And on top of the lid is convection. So that's the lid. What was it? PA6. Here that's a silicone. Here's epoxy glass. Here is a silicon. Where is the heat dissipated? No, where is it coming into existence? Heat is on top of the silicon, yeah, here. So it goes through the silicon, it goes through the die attach. We have that. Then we have the solder joint. Oh, in our case, due to the solution we selected, we have so that's silicon, that's adhesive. That's a copper. That's a SAC. Under the SAC, we have the silicon substrate. Under the silicon substrate, we have a glue. And under the glue, we have the copper zinc. In our case, I would accept that the zinc is something like a thermal ground. And that means 50 degrees centigrade. And now we have a layered system. And we make, so I write just the layers here on that, or I take that series, and we could say the following. We have a source, and the source goes into thermal resistances, and on top we have the epoxy. So that would be number one. We have the silicone. We have the PA6. And we have the number 4. which is convection. Again, that's going against ground. And what do we have on the other side? First of all, it goes through the silicon. That is number 5. Then we have the adhesive, that's number 6. We have the copper, that's number 7. We have the SAC, that's number 8. That's quite complex, complex structure. We have the silicone, that's number 9. And we have the copper zinc. Yeah, that's number 10. So that means we have something like, what did we say, 5? 6. And here we go to ground and 50 degrees centigrade. 50. Okay, that's the resistor network. And now how do we get the individual resistances? Here we make a table. And then we say we have layer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have a total. And for now we take each resistor as a brick. And then we say RTH of layer E how is it defined? It's the thickness of E divided by the area of E and divided by the lambda of E. So what did we say? That is for volumes, and for interfaces is RTH is 1 divided by AI HI, and that's a heat transfer coefficient. Okay. Yes, so we must make a table. We have the layer, the material. We have the thickness. If you do the calculation, you will have a sheet as a table. You just put in the proper properties and the values. And you have the area, and you have the lambda. Or the heat transfer coefficient, if you want. So top layer was free convection. There is no thickness to give here. We just have an area. Let's say on top of that device, it would be several square centimeters. Let's say it would be, for instance, 4 square centimeters, and that would, now we can make more. let's say 10 square centimeters just on top. What would it be? 10 times 10 to the power of -4 square meters. And the heat transfer coefficient would be something like, let's say 1 to 10. So let's say 3. Watt per square meter Kelvin. So we just do another layer underneath. I don't do all of the layers here. That would be, for instance, the PA6. The PA6, what would be a thickness? Let's say 1 millimeter. That's 10 to the power of -3 meter. Here you could take the same area as on top. So that would be 10 to the power of -3 square meter. And the PA6, what would it have? Let's say something like 0.5 watt per meter Kelvin. Here we had the silicone. Here, what did we have under the silicone? The epoxy molding compound. Say here 0.2, here 0.8. Under that, that's all, because to the lower side, we have the silicon chip. The chip is for instance, we could take some value of 1 watt per meter Kelvin. And under the adhesive, we have the copper. And copper, let's in that case take 400 watt per meter Kelvin. Under the copper, we have the SAC. There's something like 50. Under the SAC, again, we have the silicon. What could we take? Let's say something like 120 watt per meter, same here. And did I forget something? We have 5 was the silicon, 6 was the adhesive, 7 was the copper. Then we have the SAC. The silicone was 9. Now then I forgot something. That's a, yes. The silicon is 9. The silicone is 10 and the zinc is 11. So that's yes, silicone, we had something like 0.2 and the copper we had 400. Then you take proper areas. For instance, the chip would have an area of 1/4 square centimeter. times 10 to the power of -4 square meter. Adhesive, of course, has same. Copper can be somewhat larger, maybe let's say 2 times 10 to the power of -4. SAC would be same. Then we have the silicon that can already be significantly larger. For instance, 10 to the power of -3. Same should be for the silicon, and for the copper, maybe we can still spread the area somewhat. So that's somehow arbitrary values, but you can choose them according to, let's say, common sense. And in that way, one can compute thermal resistances for every layer, and you add them, but you have RTH top and you have RTH bottom, and the total RTH is you can say 1 divided by RTH total is 1 by some RTH top plus 1 divided by RTH bottom. And in that way, you get RTH. And when you have RTH, you can go into that equation here. And that means you compute times power plus TU is the temperature, and then you check if you are below Tmax. If your temperature is too high, easiest way before you change your design, easiest way is to play a little around with such data. Yeah, you're free to take a somewhat better material, and for instance, for the polymers, you always have a certain freedom, yeah, in a reasonable way, and in that way you can solve that design task. Second, with what? Yes, with the sizes, I would say, okay, you can also play. What I didn't mention here is the thicknesses. So thicknesses should be in a reasonable range, yes. For instance, when you have die attachment, you cannot say the SAC solder joint is only 2 micrometers thin or so. That's not possible, yeah. So you have certain freedom, but it cannot be excessively. But more often we have a problem that people, for instance, for adhesive thickness, use unreasonably thick adhesive layers. Yeah, that one is, it's wrong having for die attachment 0.5 millimeter of epoxy silver or so. The second is you increase your thermal resistance. On the other hand, of course, it can improve stress questions. The next thing is now here with regard to the solution is in fact it's a little strange now. because we have the following. We have that let's say that wafer level device, and it is mounted on a substrate. And normally, in all cases, we normally have different materials for the substrate and for the chip. But in between, we have some die attachment process. And now, what is the stress? What are relevant properties for stress calculation? We had that formula. The stress is delta alpha times delta T times we have delta alpha times delta T times the Young's modulus of the die attachment materials, or what was it in the lecture notes, mounting material, times the Young's modulus of the substrate times, what did we have? The length of the chip divided by, in the formula, it was an X. So that's the die attach thickness. That is the length here of the chip. It also could be the diagonal length here. And that's a formula to compute stress. Unfortunately, in our solution, we would have both CTE for silicon and for silicon, so that delta alpha would be 0. That would not be quite correct, but we could say the following. For instance, alpha of the chip is, let's say, 3 times 10 to the power of -6 per Kelvin, and the alpha of the substrate, because we have copper on it, so it will be somewhat higher. Just okay. Here we also had a factor, and what we want to select. There are several things we want to see. So the CTE here is lower. We want to see the stress after soldering. And what I would like to see is how it looks after the cooling, and probably it looks like this. Again, here we have the die attach material. So that is T is environmental after cooling, after soldering, after cooling. And also I would like to see what the stress is, and the stress here, the bending stress is larger than 0, so it's tensile. That's the reason why often the crack is coming in here into the chip. Okay, so that's how it looks. After the soldering. So about the data. So we have also seen the delta alpha is 0.5 times 10 to the power of -6 per Kelvin. What is a delta T? So that would be at room temperature here. So it's 240 minus 25 degrees centigrade. And temperature differences are given in Kelvin. And so it is 215 Kelvin. What was the length of the chip? It was 10 millimeter. Yeah. We had defined it, I think, 10 by 10. Yeah, let's take times square root of 2 because it's a diagonal. And that's 1.4 times 10 to the power of -2 meter. And what is the X? The thickness of the die attachment. What is the soldering height we typically have? For instance, it would be somewhere between 50 and 100 micrometers. So let's say 100 times 10 to the power of micrometers is 10 to the power of -6 meters. What is the Young's modulus of the silicon? It's somewhere, I think, around 150 gigapascal. And the Young's modulus of the solder it's somewhere around 50 gigapascal. And then in that way, we can compute the whole thing. Does anybody have a calculator here? So delta alpha uh, 100 times 10 to the power of -6. So it's 10 to the power of -4 that's a thermal strain, yeah, we have. And then we have 150 times 75 times 10 to the power of 2. That's 750 times 10 to the power of, yeah, that's 75 times 10 to the power of 2. That's 7.5 Yeah. Sorry? Ah, she has one. 110,000, what? For what? For the final? And the units? So already 10 to the power of -4 is something low. L divided by, that is 7.5 times 10 to the power of 3 times, what did we say, 100 micrometers? No, 10,000, 14,000 divided by 100 is times 140. 105. Haben Sie es jetzt? Do you have it? Nee, das kann nicht sein. It was here. The strain is correct. That's 10 to the power of -4. Yeah. Now, maybe you just multiply 50 with 50. Then you multiply with 10,000 and divide by 100. And then you take the square root. And then you multiply with 10 to the power of -4. 0.05. And that's gigapascal. And that is 50 megapascal. What? The C is a prefactor. Normally in a hard system, you can also, so for instance, if it's ceramic against silicon and the glass solder or such a thing, or a sinter joint, then you can take a prefactor of 0.1. Hard systems, there is, yes. In that way, I would say, anyway, we are at 50 and we are low enough. Okay. Sorry? Yeah, because it's a diagonal. So typically the chip is 10 by 10, and for the stress is not relevant along the quadratic edge, but diagonal. Yeah. Okay. It's similar in the next task. So solder joint fatigue. So here I simplify the case. We have a substrate, and that's a QFN, and for us, only the ends are relevant here in the QFN. Yeah, that's SAC. That would be in the stress-free range. What will happen? And just assume it would be stress-free at room temperature. What would be the behavior of that system when the temperature is higher? Then the substrate will expand. So we have the initial locations. The substrate will expand a little, yeah? So that's, and here it also will expand a little. So shift. And what will happen to the solder joint here, and what will happen to the device? So here we have a silicon substrate. We have a molded device on top. What about silicon? We said it has a CTE of 3. What will happen to the solder joint now? The device will become significantly larger. And in that way, the joint will be deformed in that way. High temperature. Also, I would like to see such a sketch, because how is the shear strain defined? What is a shear strain? How is it defined? So it's somehow the delta X divided by the height of the solder joint. And that is, if we take the outer length, that is the delta L of the component. We minus the delta L of the substrate divided by 2, because we have 2 sides, and divided by height. And what is it? Delta L of the component, and that is L0 times alpha of the component times the delta T of the component minus alpha of the substrate times delta T of the substrate, and that's same in our case. The gamma is L0 divided by H times delta alpha delta T, and that's it. What did we say? Delta T is, what was it in our definition? Yeah, lowest temperature, it was minus 25 degrees centigrade. So it is 135 degrees centigrade minus 25 degrees centigrade. And that is 160 Kelvin. Delta alpha. Alpha of the component, alpha of the silicon, we already had it. So it is silicon, it's molding compound, it's copper. What has a molding compound? 10. Copper has 16, silicon has 3. Let's say, take a mean value, yeah? Just 3 plus 16 is 19, plus 10 is 29, is 30. Times 10 to the power minus 6 per Kelvin. So just as a guess, as an average value, yes, of the 3 materials, so that is something you do not have to have in mind, or you don't have to calculate precisely. But if one argues that's just an average value of the different materials, then it's okay for me. And that means delta alpha is (6.5 times 10 to the power of minus 6 per Kelvin). And in that way, we have already computed some other properties. For instance, we have assumed for the die attachment of the other device 100 micrometer. That's a value we could also assume for the height. Height is 100 micrometers times 10 to the power of minus 6 meter for SAC. What else do we know? Do we have to know? We know the L0. What was the size of the device, of the controller? We didn't specify something. I think we said something like 2 centimeters or so for the size. Uh, 2 centimeters is 2 times 10 to the power of minus 2 meters and multiplied with the square root of 2 if it's a diagonal value. There is one more thing. The strain is gamma divided by square root of 3. Yeah. Now, if we have a shear strain, can we just calculate it? Just put in 2 times 10 to the power of minus 2 divided by 10 to the power of minus 4. multiplied with 6.5 times 10 to the power of minus 6 and multiplied with 160. Point 3. That seems a lot. Um, 6.5 times 10 to the power of minus 6. What is that? Six 6.5 times 1.6 is 10. 1000. Though that would be 10 to the power of minus 3, I would say, roughly. Delta alpha, delta t. And that is correct, yes. And then we multiply with L0. Then we multiply with, maybe we take it a little, yeah. Then we multiply it with 2 times 10 to the power of minus 2, yes? Sorry? Yes, and we also must divide it by 2. And we divide it by 10 to the power of minus 4. 100 micrometer was if you don't calculate it with 2. Yeah. And the square root of 3 you already took into account or not? Shear strain. So gamma is 0.2, yes, for you. No, just 0.1. Epsilon. Again, that's quite a lot. Then we have to modify somewhat because, but I think you can do that for yourself. So we had the epsilon is 0.1. And now the question is, what is the number of cycles to failures? Is we had said something like 2 times the epsilon to the power of minus 1.3. And that is 2 times 0.1 times. And that would be not so many, I would say. What can we do? We can smaller device. Lower the alpha of the substrate. lower the alpha of the component. That is the formula for Coffin-Manson for solder material. Yes. If you take 0.1 times 10 to the power of -3, do you have a value? Oh. That's not so many, huh? Sorry? 40, yeah. Still not so much. Thicker SAC. What could we get? Maybe we could reduce the epsilon or the delta epsilon. Reduce by 2. When that would, of course, you have to prove that delta epsilon is 0.05. That is 5%. What is the NF then? Yes. 49 times 2, yes. We already almost made it because we want 1,500. How can we get a factor of 10? We use an underfiller. Can we have that? Oh no, that's not possible. We cannot have it because there is no space under the device. If we would have taken flip chip, it would have, we could have had an effect because we can underfill it. A QFN you cannot underfill. So in the end, we did a tactical mistake because if we would have taken flip chip, the delta alpha between device and substrate would be very small. We could use an underfiller. It would be much easier for the thermal calculation because we do not have 11 resistors to take into account. Yeah. So in the end, yes, here the problem is in that part of the solution. Of course, we get a result. The result is correct. All is fine. The only disadvantage is we don't achieve the 1,500 cycles. And I would say with that design, it is hardly possible. And with that design, we could lose the 2.5, 2.5 credits we get for reaching the target. Yes, that would be a disadvantage. I would say yes. That's not the optimum solution, but at least you know how you can improve that.
I have a question.
Yeah, go ahead.
And in the task before, we have had a problem that we have silicium chip and a silicium substrate.
Yeah.
And there was the CTE too similar.
Yeah.
Why do we have now the problem that that the device won't last as many cycles?
Yeah, your question was in the previous task on the stress, we had a very low delta alpha. In fact, I constructed it a little artificially to have something. But here it is the case we had selected a QFN device, and the QFN device has a CTE of roughly 10. Yes, that's a fact. And on the other hand, initially we had selected a silicon device, and for the substrate, and so we have a relatively high delta alpha. Yeah, and that's one of the reasons why we have a problem here. Again, maybe also I would recommend that you recalculate the strain so that it is really 0.05 as an absolute value. Also, what is in the QFN here, what is a little different than, for instance, when you would have taken a BGA, just the height of the solder joint is significantly lower in a BGA if it has, let's say, a ball diameter of 0.5 millimeter. It has a height of roughly 0.5 millimeter, or if it's 0.3, as a ball size, the height will be roughly 0.3, and that's significantly more. And yes, in that way, it was just a combination which as a product of several factors led to such a high value. What else could you do? For your design, for instance, one straightforward possibility could be you just say, I don't take silicon as a substrate. Yeah. But on the other hand, if you wouldn't do that, then the other calculations would all be affected. So it's always important to have a good concept from the very beginning, because you cannot go iteratively through all of your exam to improve it. Okay, let's address the last question. The longest digital conductor line is 72 millimeters. And the question is, what is the time of flight of a digital signal, and whether we have to apply the transmission line model? time of flight, and do we need a transmission? What is the time of flight of a digital signal? The speed of a signal v is speed of light divided by square root of epsilon r. And yes, the time of flight is the length of the line divided by the speed. And that is the length divided by speed of light multiplied with epsilon r. Yes. So what's the time of flight here? What did we say? 72 millimeters times 10 to the power of -3 meter divided by 3 times 10 to the power of 8 meter per second. And what is the epsilon r of the silicon? Does anybody have the value, or can anybody look it up in Google? Permittivity of silicon? How much? So let's say 12. Huh? Square root of 12 is 3.5 or so, huh? Yeah, I would say. So it's times 3.5 divided by 3 times. That's 24. Anybody have the value? 72 times 10 to the power of -3 times 3.5 divided by 3 times 10 to the power of 8. So it's 8.4 times 10 to the power of -10 seconds. And that is microseconds is nanoseconds is times 10 to the power of yeah. So what is it? 840 picoseconds, I would say, huh? That's the time of flight. Sorry? Picoseconds is smaller than 10 to the power of 9 minus 9 is nanoseconds. So that's 840 times 10 to the power of 12. And 10 to the power of 12 is picoseconds. So it's 840 picoseconds. Okay. What is a transmission line model? We have a conductor, and then we have a signal coming, and the signal has a leading edge. Yeah. And if half of the leading edge is more than the length of the line, then we have a transmission line model. Then we must apply it. Yes, if half of the rising edge is longer than the length of the line. So if LA half is larger or equal the length of the track, then we must have a transmission line model. And now the question is, what is the length of that leading edge? And roughly we can say the time of A is roughly 7% of the inverse of the clock frequency. Question is, what was the clock frequency here? What was our clock frequency here? We didn't specify it, so you give me a reasonable value for a microcontroller. What is the clock frequency? Louder? So now you should be able to hear me again. Okay, with that data, you can use the formula we have. The time the rising time is, of course, quite simple, because the time A is just the LA multiplied with speed, or LA is just TA divided by speed. And the speed we already calculated. And in that way, we get the LA value. Yeah. And the TA was 0.07 divided by megahertz is 10 to the power of 6 divided by 10 to the power of 8. And that's in second. And that's 7 times 10 to the power of that's 7 times 10 to the power of minus 10 seconds. Okay, then again, it's in the picosecond range, and then we can compute the LA. And when we have the LA, we can decide, do we need a transmission line model or not? Okay, is and what was the speed? Roughly 10 to the power of 8, in our case, meter. No, that was nonsense. The time that would be correct. So I mixed it up. Ten to the power of 8. And LA is roughly 7 times 10 to the power of minus 2 meter. Is that correct? That would be 7 centimeter. And that is just 70 millimeter. And 35, so is smaller than the 72 millimeter. That's a half of the rise time. In that case, I would say we would not have to use a transmission line model. Okay. In that way, we are finished. And in that way, we should have solved all of the exam questions. Do you have questions now? Yeah. Yes, yes, yes. That's been the way, yes. But you don't have to know them precisely, but let's say as a reasonable order of magnitude. Yeah. So there are
What was
many
the question?
materials which are very similar. And so in that way, one can estimate how the values are, or if your assumption is reasonable or not.
What was the question?
No, it's not given. It's just if you exercise, you can use such data.
Sorry, can you maybe repeat the questions? We don't hear them online.
Yeah, I put it on the Ilias, of course. Yeah. Oh, yes, it will be also if you go to Ilias. Unfortunately, I could not record this, but from the previous years, the solutions of the exercises, you also have recordings. I checked it, and you find it all on Ilias. Yes. Sorry. Yes, if your design is possible that way, of course, yes. You are the designer, you're free. As long as it's reasonable to me, it's okay for me. Yeah. So let's have a look at Ilias. You have my email address. I still have something to answer for you. Oh, it worked. Yeah, here it's assembly and packaging technology. Here we have recordings of lecture. That's from previous lectures, all of files. We have recordings of exercises. Again, all of that was recorded in 2020, but there is not so much difference. Yeah. You have that. We have the lecture notes you also have, and then we have already all PDF of all previous exercises. Some are similar like this time. And in addition, we will now have the exercise of this year here. Unfortunately, I still have to play around a little because I had to shift with the data formats. Yeah, here. Sorry, what? You're right. Yes, you're right. I have to check it. I put it on. Yes. Yes, but that's on Ilias. You will have it all together. It's in fact, there is already plenty of stuff to start to prepare. Things didn't change very much. Yeah. And in that way, my proposal is you do several exercises and you do them in a group. That's better than doing it alone. Maybe also you have to check a little with the time you have. What was the time? I think 180 minutes you have for that. And in that way, it is possible to solve it in that time.
I think for the exam, we are not allowed to bring anything except.
Also, what should be exercised when you write some things? Don't write, especially in the explanations, don't write too many novels. Yes. There are sometimes people, they write things which were not really asked and about the philosophy of assembly and packaging and so on, that's not asked for. On the other hand, if you write such things, you're missing the time for answering properly the other things. And in that way, the things you do and the answers, you must exercise a little as short as possible, but on the other hand, having all of the relevant information in it. Yes. Also, when you exercise, maybe it's better to make a simpler design. Yes. And for instance, when you take a substrate, what is always good, maybe also not a too complex substrate. Thick film technology is always something good. Yeah, it's simple. Materials properties are in the middle. Yes. So for all the problems you want to solve, thermal stress, CTE, it matches all quite, for instance, or similar with LTCC. LTCC is maybe a little more complex to describe, but on the other hand, it's also possible. And in that way, normally I don't give the task that you also have a specific substrate or so. Yes, you're free. So let's say under commercial aspects, it probably wouldn't be the best solution, but it's the best solution you can achieve in 2.5 or 3 hours. Yeah, that's the point. Yeah. Okay. Sorry? No, that was not a question. If the question would be, in the case you draw the transmission line model or the capacitor resistor model, but that's not was not the question here. The question was just what is the time of flight and do we need it? Yeah, so you check, and what you also do, that's also quite a number of people forget it, to say explicitly we need a transmission line model or not. Yes. If you would write down first the condition and then have the result, yeah, but anyway, you should really specify what is, do you need it or not? Yeah, that was my question and I wanted answered. Yeah. Yes, so there is a question for the exam. Are we only allowed to bring a calculator and a colored pens? No cheat sheet. No, definitely not. and the colored pens, any color, as long as it is black. No, black, that was for the Ford Model T. You can have any color except red color. That's my privilege, because I have to correct. Anyway, you can use orange or pink or whatever, but not red. Yes. Also for the design task, it mentions the conductor line length and the frequency of the analog part. Could you please let us know how we should address these in our solution? Okay, we have seen the solution, the frequency. If it was not given, but if it's needed, you must make a reasonable assumption. Yeah. Maybe you write down typical frequency of microcontroller or of single processor or such thing, 100 megahertz. So I do not. In that case, I just want to see you have some idea. Okay, could you please record the rest of the exercise? I would say we have recording of very similar exercises. So unfortunately here I was not able to record it due to technical reasons. If I would have had more time, I wanted to do in the other room, but here we had to go along. Okay. I wish you good luck for your preparation, and we will meet on, I think, September 13th. Yeah, yes. Okay. I know 9, my holiday is ending. So, okay. Yeah. Okay. That's for this year. And hope to only meet you once again in that exam and not in an exam for a second time. Yeah. Okay. Let's stop here and goodbye then.